So chapter 10, 11, and 21 I grouped together because they have to do with organic synthesis. The chapter 10 is going to focus on reactions that transform the functional groups, like, for instance, hydroxyls, any of the hydroxyls or the halogens, even cyanide is considered a functional group. Ethers, right, or aldehydes or acids. Those are all functional groups, and this chapter is going to focus on reactions, synthetic procedures that had to do with functional groups. Chapter 11 is going to talk about modifying the carbon backbone, right, extending or decreasing the carbon chain. And your handouts include tables with reactions.
Yeah. Please.
They came straight out of your book. Yeah. I just compiled them into something. And what I'll do is, for the exam on this material, all of those will be in the back of the exam, so you can refer to them. All right. Also, during these chapters, we want to look at things like reaction conditions that favor one type of reaction over another, and pitfalls. In other words, I like to think of them as dead ends, right? You think, if I put this together and this together, I'm going to get this product, but the idea is to recognize when those reactants won't give you what you think you're going to get. All right. Let's see. I may have covered some of these already. We're going to focus on the SN and the E type mechanisms, but the reactions, we follow a different protocol, not protocol. Syntax. How about that? We follow a different syntax when we're writing out a synthesis as opposed to a mechanism. Right? We've done mechanisms so far with the curved arrows and all that stuff, and we're still going to use them to help us understand what's happening in a synthesis. When you write out a synthesis, you design a synthesis, you want to set it up almost like a recipe. Like, this is the actual compound that goes in. We're not going to take any shortcuts and throw out spectators. Right? Everything's there that you need as a synthetic chemist. All right. Let's see. Okay, so when you're designing a multi-step synthesis, as required, we're going to add some reactions along the way. Right, so our starting point is going to be the SNs and the E's, but we have to pick up some. Actually, we'll go back to some of those earlier reactions, the elementary steps, and they will enter into the reaction to give us the product that you want. I mean, we call it retrosynthesis. In other words, you start with the product that you want, and then you work your way backwards. And that eliminates a lot of dead ends. Okay, let's see. All right, hopefully along the way, as we introduce different problems, that patterns will begin to develop, and you'll be able to apply certain of the elementary steps and mechanisms to help understand how to get to where you want. I mean, that's the hope. Okay. So this is an outline of the chapter. We're gonna look at the language of organic synthesis, that syntax I was talking about, how to write the synthesis so that you can communicate to anybody else that reads it what they need to do to end up at the same place you did when you designed it. It's also a good idea to catalog your reactions. This is a personal thing along the way. When you develop one, when you go to a lot of trouble to design one of these syntheses, you want to have it documented so you can go back and do it again later. All right, and there are various those are specific syntheses, and we'll go through those one at a time. All right. Okay, here's the language of an organic synthesis. You have a target, right? That's the end product that you want. And you have the steps of the reaction set up so that you can follow it like a recipe. Anything that's not the final product is called an intermediate. So reaction 1 will produce an intermediate A, and then that'll go into a reaction. You probably add other reactants in there with it, but that's your starting material. And then you modify that one, and it goes to intermediate B, and then you'll change conditions. You'll add other reactants and end up at your synthetic target eventually. Now that's a very, very oversimplified version because most steps in a synthetic series will produce it may be something as simple as just producing not very much of your target, right? 10 or 15% of what you expect. And then you've got to clean it up before you can go to the next step. Hopefully, if you design your synthetic pathway correctly or to your advantage, then you won't have to do a lot of cleanup between steps. In other words, the second step in the reaction, say, will just ignore all that other stuff that's in there. That's one way to, well, it does two things. It reduces the number of steps and cleanups you have to do, and it increases the overall efficiency. Because the more steps you have, the lower the overall efficiency. You're never going to have 100% efficient conversion at each step. So they kind of compile. So the fewer number of steps you can put into a synthetic pathway, the better. All right, here's convention number 2 when you're writing writing reactions for an organic synthesis. You want the overall reactants. In other words, what are the actual materials that you're going to use? Right, so we've named the 2-phenyl-2-tosylpropane, tosyloxypropane, and potassium bromide. Now, potassium probably doesn't have anything to do with the reaction. We're focused on the bromide ion, but in a recipe, you want to know the material that's going in. So we say, all right, we're going to put a potassium bromide, and we expect the overall product to be 2-bromo-2-phenylpropane. And then you want the reaction conditions. And those, let's see. Well, I thought the reaction conditions would be in there. I guess they're going to wait. Okay, here's one. Okay, all right. I'm getting ahead of myself. So we got the overall reactants that go in. Then we have the overall product that comes out the other side. Now, this is after you've decided what your product is going to be. And then you look for starting materials. Sometimes you can go all the way back to the very beginning and say, all right, I want to go from this starting material to this overall product. How do I get there? It may be very simple. It might be a 1 or a 2-step process. But if it's multi-step, then you may not be able to use the reactant that you think you do. Because when you work backwards through it, you may find out that a different reactant would work better. But this is a starting point. This is what you think that you're going to do. Go from these overall reactants to the overall products.
Is there any like instances where like you have the overall product and like the starting point, they just don't add up at all?
Mm-hmm.
Yeah.
Yeah. Oh, yeah.
So you have to just start from scratch again.
Not necessarily. It depends on where that glitch occurs.
Yeah.
If you're working on a retro analysis and you're working backwards through it, usually you can eliminate a lot of those pitfalls. And then we're not even considering the possibility that you want this reactant for your procedure, and either the reactant's not available or you have to make it. That happens a lot. You have to make the starting material. Or it's so expensive you can't afford it. So there are other issues that we're not even considering in this discussion of synthesis.
I guess there's just a lot more that goes into it than what goes through my head. Like in my head, it's just
Yeah.
something like they just look at and they know,
No,
and it
no,
just works.
very, very few. I've never met a chemist that could do that.
Yeah.
I mean, some of them are pretty good,
Yeah.
right? And from experience, they know what to avoid and which
Yeah.
direction to go. But nobody that just hasn't a perfect intuition,
Yeah.
not like they do in the movies.
Yeah. Now with pointing arrows, like, because this, kind of ties in a little bit, can somebody just look at that like and just immediately know what it is, or do they have to like slowly work it out, or can they just like look at it and know?
What's the question?
So like when you're looking at the problem and like you're doing the pointing arrows, like how like we have to like work it out,
That's a mechanism. Yeah.
the mechanism, can they just look at it and automatically know, or do they also have to work it out?
From experience, they'll usually know how the mechanism works.
Yeah.
But in the beginning, if you're a student starting out, it's going to be a great mystery.
Yeah.
It's still a mystery to me because I
Yeah.
don't use it every day.
Yeah, it is hard.
So in order to see if the proposed starting material ends up with the product, then we look at the mechanism to help us understand what needs to happen. And if we say, take that example that we just had, this tosylate is a good leaving group. So an SN1 reaction is very likely. And that tosylate's going to leave a heterolysis, that's elementary step, and then leaves behind a carbocation. Then the bromide from the potassium bromide can attack it and form the bond. Okay, that's what we think should happen. This would be an incorrect synthetic step. If you simply wrote the bromide in there, that's not the way bromine exists in a recipe. It's always potassium bromide or sodium bromide. It's got a counter ion to go with it. So we wouldn't write it that way. That's the way you would write it for a mechanism, but not for a synthetic step. Similarly for the hydroxyl in the bottom elimination reaction. you would not write it that way. The hydroxyl would have to be something like potassium hydroxide or sodium hydroxide, strong base would give you the hydroxide ion. So when we write the synthetic step, we don't have any loose charges floating around. Okay. Now, well, there's our sodium hydroxide, of course. This is by convention. Byproducts from a reaction and leaving groups are not critical to the synthesis, and they're often omitted from the written synthesis. So this 2-bromo-3-ethyl 2-methylpentane reacts with sodium hydroxide, which provides the strong base. Right? Elimination reactions require strong base. Substitution reactions require a nucleophile. Sometimes they're the same, not always. So we have those two reactants, and the product will be 3-ethyl 2-methylpentoene. Now, what happened to the bromide? It's not essential to the reaction, so we just omit it in the products side. All right now, this is convention for organic chemists, right? I'm a more inorganic chemist, and we like to keep track of everything. Organic chemists don't do that, right? This is one convention. When the bromide's done its thing and it's left, it's a leaving group, forget about it. The only time you put it in there is when you have a mechanism that you're trying to explain why it happened. Water is also a leaving group. Let's see. First, this would probably be an E1. The bromide would leave, producing a carbocation. Then proton transfer to the hydroxyl, the base, the hydroxide ion. A hydrogen from that. Let's see. It's kind of hard to see from back there. Get my arrow going. Can I see my arrow? I don't see. There it is. It's kind of jumping around. Okay, come on over here. Here, there we go. So the hydrogen that leaves, that's picked up by the hydroxyl, comes from that carbon right there. Disappeared again. So the point is, with an elimination reaction, we get the bromide is a leaving group, produces the carbocation, and then the hydroxyl comes in and picks up the hydrogen from that beta carbon, and the electrons from that hydrogen, the bonding from the hydrogen, those electrons go into a pi bond, and that's where you get the double bond. So the products that are left out of this synthetic step are bromide ion and water. Okay. So let's see, convention number 2. Very often the reagents and the reaction conditions, well, actually, they should be specified. What reagents? What's the solvent? What other reagents are involved? In fact, this sodium iodide isn't necessarily put into the reactant side as a reactant. We'll put it on the reaction arrow. So it is a reagent. It's part of the reaction, but we put it on that arrow just because it's convention. And then we have to identify the reaction conditions too, right? All this takes place in acetone, which is considered an aprotic solvent, right? There's no hydrogen bonding in acetone. And it's conducted at 40 degrees Celsius, so it's slightly elevated temperature, and it takes 3 days. Right. So those are the reaction conditions in this single step to go from 7-chloroheptuonene to 7-iodoheptuonene. All right, here's another example. Sometimes the solvent is not just a solvent, it can also be a reagent. In this case, the methoxy replaces the bromide. So it's a solvent. Methanol is a solvent, plus it's a reactant. And we're not specifying that it is. We just deduce from the fact that we've got an ether as a product. So it had to come from somewhere, and those are the only things that are in there. It had to come from the methanol. Now, we didn't say anything about the mechanism, how it got there. That was just a synthetic step. Now, if you have more than one synthetic step to go from overall reactant to overall product, then we'll number them. And so the first step in the reaction is with this sodium hydride. So that hydrogen is going to come off, it's going to be like this. Whenever, I don't know if you remember from general chemistry, but hydrogen usually has a +1 charge, right, in a compound. But when it's paired with a metal, then it's like that. So this comes off as a negative ion. And that's what facilitates one of the reactions, step one. Then after that reaction is complete, and we do whatever we have to clean it up, then step two introduces methyl iodide. And when we do that, notice 1, 2, 3, 4, 5. There are 5 carbons, pent 1 ion, and we're going to make hex 2 ion, right? So the triple bond is going to stay put. It's not going to move, but we're going to tack a carbon on the end of it. Now this sequence of steps did not, we're not dealing with functional groups, right? We haven't got to that point yet. Here, this is actually adding a carbon to the backbone. So you got that methyl group stuck on the end, right? But the point here is 2 steps, and we number each step. Now, if there are conditions that go along with each step, then we add those, we put a slash, and then the conditions for that step. Right? There's a reagent, and it's in the dimethyl sulfoxide is the solvent. And then we go to the second step, where we have bromine in aqueous solution. And that completes the second step produces the desired product. Sometimes they use a comma. I don't have a preference. I think they tend to use a slash in this textbook. Okay. All right. So let me see. I got this in my way. I gotta move it so I can see. Okay. So here we have this is one of the reactions. This table 912 came out of chapter 9. Is one of the reactions where we alter the carbon skeleton. We start with an alkyne, and by convention, that amber shading shows you the carbon that's where the attachment's going to occur. That's a starting compound. And then we have the conditions. It's a 2-step process, and we're going to attach where the hydrogen used to be. We're going to attach that R group. R groups usually mean carbon, at least a methyl, probably more. So we've extended actually, that's what we just did, right? In that previous reaction. But this came out of chapter 9, and I've included that in, yeah, in that, right?
So what is the difference between the R and the apostrophe and then just the regular R?
Just to show you that they're not the same.
Oh, okay.
Yeah, that's the only reason. If there's another R that comes in there, it'll have maybe an R double apostrophe.
Oh, okay.
And then these tables identify what's the electron rich species and what's the electron poor species. So the electron rich species is derived from the alkyne when the hydrogen is removed from the alkyne to form H2. So this R, C, D, H, then we've got this one right here. This one has a lone pair that attacks that, forms a bond, and you get hydrogen, probably a gas. So you're going to see bubbles in your reaction. So what happens to this lone pair here? It just stays on that one. Now we get that. And that makes a reactive species, the alkynide anion. So that's the electron-rich species we produced in the first step of our synthesis. Then in the second step, we have this this other group with a halogen on there, chloride or bromide, probably. And then the second step is an SN2 reaction. So if this is going to be the electron poor, this is the electron rich, this is electron poor. So this one is going to attack that one right there. And then those electrons go here, and we end up with our halogen out there, chloride or bromide, and form the bond here with that R prime. So that's the mechanism that's behind these two steps. All right, here's a different set of steps. This has 1, 2, 3, 4 steps in this reaction to go from hex 1-ene to 2-ethyl hexane nitrile. So we're not extending the carbon chain, right? It's still 6 carbons, but 1, 2, 3, 4, 5, 6. No, we do have 7. 1, 2, 3, 4, 5, 6. We have extended the carbon chain. We added a methyl group in the second step. So we convert the functional group. Functional group would be the ene part of the molecule. We convert it to an epoxide, right? Because we add oxygen in there on that double bond and form that strained epoxide. That triangular part of the molecule is extremely reactive because of bond strain. Right? Those bonds would prefer to be 109.5 degrees, right, in an sp3 hybridization, but we've got them bent to 60 degrees. That's a lot of strain. So that epoxide then is very reactive. Actually, there's 1, 2, 3, 4, 5 steps because we've got 2 steps with the B intermediate. Step B. So that top one, that number 1 in red, that's a Grignard reagent. You'll see those a lot, and they're used to add carbons to a backbone. What they do is let's see, they're using, yeah, magnesium. Okay, so when you do that, you make this deficient, I believe. Let me see. Is that what it does? Nah, I better not. Forget that. We're gonna have a slide on it anyway. So I don't want to confuse me and you both at the same time. So this is just an example where you see all of the different conventions that we've discussed so far put into a single or a series of steps. Here's some more functional group transformations where we have an alkyl halide. It looks to me like this one is a primary. The first one is a primary alkyl halide. So they have a chloride or a bromide probably on that, on the number one carbon. And the second one is working from an alcohol. So it looks to me like if there's a carbon involved, it's going to be blue shaded. If there's not carbon, it's going to be amber shaded. Let me back up and see if that's correct. No, can't say that because that carbon is amber shaded. I'm not sure what the convention is then. Let's just call those active sites. That's where to focus your attention. So if we go from a primary alkyl halide to an ether, we will use the sodium salt of a strong base. Nucleophile, no, nucleophile. And the reaction itself is SN2. The second one with an alcohol to produce an ether. So we're getting an ether out of both of these. Let's see. It says these are discussed in chapter 7, 8, and 9. Okay, take their word for it. They must, elementary steps. SN2s are elementary steps. SN1's not. So I'm not sure what they're getting at there.
The alcohol on this one's a little different from that one on the board. I mean, it's just like different.
Functional group transformation. Okay, it's number 4. Yeah, number 4. Oh, that's different. Function. Oh, that's 10-1. This is 9-11.
Oh, okay.
Yeah. Is that it? No, that's 21. Yeah, find 9.
No, I don't have none. Oh, wait, there's backsides. No, I don't have it. I mean, it's on here, but
Yeah, you should have a copy of it. And 12. I forget to put that in. Let me look at my copy. Okay, let's see. There's 10. There's 10. Oh, that didn't. Got them out of order. There's 9, 12. I don't have it. All right, that's a boo-boo.
that's okay.
Yeah, I'll have to make a note. I need table 9, table 9, 11. Let's see, that's 4 and 5, so there's probably more to that table.
Yeah.
there's 912. Table 912. 912 is in there, isn't it?
Yeah.
Yeah, there's 912. Okay, I forgot to put in 911. Functional group transformations. Or is it included in a different one? Let's go here to this one. Functional group transformations. Alkyl halide. Yeah. It's included in 10.1. It's a little bit different though.
Yeah, yeah, that's what I was saying. That it's a little
Yeah.
bit different.
Right. Maybe that's why I didn't include it, because it would be duplicating it. Okay.
So on
Yeah.
10.2, it's like has like both the R's highlighted. So why isn't one R prime and the other one? Like they're both just
Let's see. Huh. Maybe they're saying, oh, this is asymmetrical, right? This one probably has more carbons in it than that one does, or vice versa. But these two R's are exactly the same.
oh, okay.
Yeah, that's what that means. There's a difference. The way the reaction proceeds depends on whether it's symmetrical or asymmetrical. And I suspect that has to do with the carbocation intermediate, because the less substituted side will be, well, actually the more substituted side with carbons, like if it's a tertiary carbon, it's going to be a more stable carbocation. So that'll influence which direction the ether is going to form. Okay, so we got the symmetrical versus asymmetrical here, and Williamson ether synthesis. All right, this is the first, in this chapter, this is the first named procedure. And we've got two reactants here. We've got an alkyl halide, a primary alkyl halide, and then we have a oh, now it's gone blank. I don't know what to call it. We've got the other compound with the sodium, which means that attached to the sodium is going to be a strong nucleophile, because once the sodium is a spectator, so that means that oxygen has a negative charge on it, and it's going to attack the carbon next to the bromine. Like, what have we got? 1, 2, 3, 4. 1, 2, 3, 4. Bromine here. So this one's going to be slightly positive because of the withdrawing effect of the bromine. And then we've got this compound. Let's see, 1, 2, 3, 4. It's going to be negative.
There's the sodium.
I know.
Oh.
Yeah, I'm looking at the mechanism now.
Oh, okay.
Right. Yeah, that's the correct way to write it. But this is going to be this is the electron rich. This is the nucleophile. This is the electrophile. And this is probably going to be an SN2 mechanism. So this one, this electron pair is going to attack that. So we're going to get bromide ion released, and we're going to form a bond between this oxygen and that carbon. And that's where we get the 1-butoxybutane or dibutyl ether. This is a symmetrical ether. In other words, you got 1, 2, 3, 4 carbons on this side, 1, 2, 3, 4 carbons on that side.
Does that mean it's more stable if it's symmetrical?
Not necessarily. Symmetrical ethers symmetrical ethers. I think the term there is regioselective. Symmetrical ethers are not regioselective in subsequent reactions. Right. We've created a symmetrical ether here. I mean, that's just the fact of the Williamson synthesis and the mechanism. We can also make an ether with as a condensation reaction. So a condensation reaction is one in which two molecules come together at the expense of the loss of a smaller molecule. And in this example, butane-1-ol in acidic solution and with heat will form the symmetrical butoxybutane. It'll form exactly the same product, but it's by a different mechanism. And it's going to be symmetrical because the butane-1-ol is both the reactant is two reactants. The same molecule is one is the attacker and one is the recipient. So the mechanism says it happens by a different process. It's a multi-step procedure. You have in acidic solution, we're going to protonate the hydroxyl group on the end. So instead of, okay, hold on a second. Well, we have different reactants. Different reactants. We've got the butane-1-ol rather than the 1-bromobutane. So the butane-1-ol, let's erase this. Butane-1-ol, that hydroxide is not a good leaving group. It's a good nucleophile if you can get it out there with OH minus. It's not a good leaving group. So we have to modify it. And that's what the acid is for. The acid, let's see. OSO3H. The acid, this alcohol, actually, we do a proton transfer there. And then we make this molecule here, OH2 plus. That's water. Water is a good leaving group. I think we studied that in the last chapter. Right. So now that we've got a good leaving group, we can come in with another one of these. Right. This is the nucleophile now, and this is the electrophile. And this one now, this is going to be slightly positive. This one can attack that. This one goes over here, and that leaves as water and forms a bond. There. So we get the same product as before. Well, hold on a second. I forgot there's a hydrogen here. So when we form that bond, we have an extra hydrogen and a positive charge. So when we form the bond here, we have a positive charge. And now what we have to do is another proton transfer. And that occurs with this water molecule. Takes this, let's see. Yeah. It forms bond there. We get the hydronium on it. And that removes that hydrogen and takes the charge with it. Well, it leaves the electrons behind. So this is a, let's see. Yeah, it's proton transfer. Okay, so there's several steps in this mechanism, whereas in the previous one, there were only one step, two steps. But we come out with the same product. And this is a condensation. Condensation where two molecules come together at the expense of the loss of one molecule. That one.
So in these cases, are these like these past three? So these where you would start out with the starting product and end up with the same one? Because if you have the reaction that you want, wouldn't you just choose the easiest one?
Let me think. This is a mechanism. So as far as a synthetic step goes, this all happens in one step.
Yeah.
One synthetic step. Whereas with the previous one, it happened at one synthetic step. Yeah, both of them do. A single synthetic step, we have several elementary steps. But as far as the reaction efficiency goes, there are other factors that feed into that.
Yeah.
Not the multiple steps. It's not a multiple step synthesis. It's a multiple step mechanism.
Yeah. Okay. Yeah.
Yeah.
I think I'm getting those two combined into one.
Right. Now we're actually given the percent recovery here, 91%, which is really, really good. So I'm thinking that this condensation reaction is probably more efficient.
Yeah.
And the reason that you can create this here, this hydronium, and it's stable, is because it's a strongly acidic environment. Right? It's got sulfuric acid in there. So we're not competing like we did in a previous chapter. We're not competing basic conditions in an acidic reaction, right? That kind of cancel each other out. We're copacetic, right? We've got the same acidic conditions here. Okay. I'm taking too long here. I know I am.
Well, I keep asking dumb questions.
Well,
so.
no, that's all right. I just, if you understand it, then I put that back here and say, that's a good way to approach it the next time I do it. Okay, limitations of ether synthesis with condensation reactions. Okay, here's one of those pitfall things that I was talking about before, right? Which one of these would be best? If you can get 91%, you'd like to do that reaction, but will it work? The problem, that was a symmetrical ether that was formed. If we want an asymmetrical ether, in other words, we want an ether between a, say, formed between a propanol and an isopropanol on the other side. Well, that's the trivial name for that is isopropyl propyl ether. Can we produce the product that we want? Well, if we put the isopropanol and the normal propanol in there together under these acidic conditions, are we going to get the desired product? We're going to get a mixture. We've already seen one of those is the symmetrical ether. Right, that 1, 2, 3. The propyl ether is that first red one on the right. And then you could also get a reaction between the isopropyl, and you could have isopropyl ether. Those two symmetrical compounds will be byproducts. And the desired one, you'll get some of it, but you'll have a mixture of those three ethers. So that's the problem with using this condensation step to generate the product you want. Okay. I danced around that one. Did it make sense?
Yeah.
Okay. So we've got a problem here with forming symmetric versus unsymmetric ethers. We can produce both symmetrical and asymmetrical ethers by the Williamson ether synthesis because we can be regiospecific. In other words, when we have that primary halogenated compound, and we react it with a propoxy ion, anion, then we get the ether that we want. We don't have any of those side reactions. Now, if you don't care, right, then it might be easier to do the condensation, but the Williamson synthesis will give you the product that you want. It may not be as efficient, but you won't have to deal with any of those side reactions. Okay, there are limitations on the Williamson ether synthesis, of course. So here's one of them. If we try to form, what we want to form is an ethyl isobutyl ether. Ethyl on the left-hand side, isobutyl on the right. We try to form that ether from reacting 2-bromo-2-methylpropane, or let's see, that's not isobutyl, it's tertiary butyl. Tertiary butyl bromide would be the trivial name. 2-bromo-2-methylpropane is the proper name. You try to react that with in ethanol with the ethoxy ion, then you don't get the ether. In fact, the E2 mechanism is preferred in this case. Right? So the E2 means that, let's see, well, let's see, what's the mechanism? It can be used to produce lots of different ethers, but the reactions has the same limitations as any SN2 reaction. Steric hindrance makes SN2 reactions unfeasible for tertiary substrates, right? Because that ethoxy ion can't get in there and attack the carbon attached to the bromine. You see which one I'm talking about? Okay. Steric hindrance keeps it away. So the next thing it would do would, instead of attacking the carbon, it would attack a hydrogen. And in the process, 1, 2, 3, 4. Yeah. So we've got this, and this, and bromine here. Right? This is a methyl group. There are no hydrogens on this carbon, but there are hydrogens here, here, and here, and here. So, and they're all the same, right? So pick your, it doesn't matter which one. Right? So you got these hydrogens here. So that there we go. That one is going to proton transfer. Right? And then this let's see, is that what I want to do? No, it doesn't go to that carbon. These electrons go here and form a double bond. And then this one leaves because we can't have more than an octet on that carbon. So then that bromide leaves. And we form a double bond here with this one. This one's still here. This one's still here. You got a double bond here with that carbon. And so we get ethanol. I think that's why the ethanol is the solvent, because in the reaction, we're going to produce ethanol. So that's an E2 reaction. It all happens in one fell swoop. That hydrogen plucks off, transfers electrons, makes a double bond, and the bromine leaves. So we're okay. We've got 1, 2, 3 arrows. We didn't exceed the 3-arrow rule. Okay. So now the question is, devise a Williamson ether synthesis that would produce the ether shown here. Right? We got this one instead of the one we want. And the one we want would be, let me draw it the way it's. We want an oxygen there. Yes. And then we want like that. That's what we want. We don't want this. So can we do it? Well, we're going to get methylpropene. If we do it the way it's presented there. So because the substrate is tertiary, the steric hindrance will prevent the nucleophile from attacking that carbon. It won't attack this carbon right here because it can't get in there. The Williamson synthesis does require an alkyl halide, which we got here. There's an alkyl halide and an alkoxide. That's the term I was looking for. The alkoxide anion as the nucleophile. So oh, I get it. Yeah, I get it now. Here's what we do. This is the attacking group. We just switch it around. We put the bromine on this one. Right? Yeah, put the bromine on that one. And we make this one the alkoxide.
So then the bromine attacks the oxygen, or the oxygen attacks the bromine.
So now it can attack this secondary carbon.
Mhm.
There's not as much steric hindrance. So we can attack this carbon here.
Yeah.
And that can go over there and we form our.
Yeah, because the bromine leaves.
Yeah, we just switch places with her.
Yeah. But we don't do anything with, I guess, the carbon up there, correct?
Well, no, I've left all that garbage there. It's just a methyl group. Yeah.
Okay.
I mean, it would be in the way, except that now we don't have as much steric hindrance around this carbon. So we do get the product we want. I suspect that it's still not very efficient, or it takes a long time to do the reaction. But at least we get the product we want. Here we go. All right, how far along are we? Am I going to eat up our lab time?
One set 25.
Okay, we're about a third of the way through.
Yeah, 25 was 75.
So, how can we design the synthesis of an unsymmetric ether shown below? All right, so we've got this benzyl cyclopentyl ether. Right. Can we do it with the benzyl chloride and the cyclopentyl oxide ion? Can we do that? All right, so let's look at possibilities. All right. Is the R group primary? It doesn't specify. Starting compounds. Typical SN1 or SN2. All right. So I think what we're getting at here is if we're going to do the reaction with that bottom set of reactants, we're going to take our benzyl alcohol and convert it to a chloride. And we're going to react the pentanol and react it with the hydrogen ion. And that will create the cyclopentoxide ion. Then we can proceed with the reaction, the final synthesis. So we had to do those two previous steps. That's what this one shows. We had to do the step for the benzyl alcohol. We had to convert it, and then we had to convert the cyclopentanol, and then the reaction can proceed. So that's how we'd write the synthesis. All right. I think that was the gist of that procedure. It was just to say that if we want to get if we want to produce an ether, we have to have shoot, hate it when that happens. We have to have an alkyl halide. Actually, well, I guess we could call it an alkyl halide because it's bound to the carbon that's not on the ring. We have to have an alkyl halide and we have to have an alkoxide. So that's what we had to go through, those two first conversions to get there. And if we were designing this reaction to get to that point, we would start with the end product and we say, okay, we need a reactant on one side. That's the alkyl halide. And then we need the alkoxide on the other side. So it depends on which one. I guess up to this point, we've only learned that steric hindrance is a problem. So we have to decide which one has the most steric hindrance, or which one would produce the, where should the chloride go and where should the alkoxide go to get the best outcome. Okay. So if we have to convert an alcohol into an alkyl halide, this is the best way to do it. Right. Let's see, did we show it earlier? Well, we used hydrochloric acid. That's not a very efficient way to go. I mean, it can be done, and it takes 4 hours in heat. Here we're making a bromide. And those are the steps. You've got a proton transfer and SN2 reaction to get to the bromide. Okay. But the problem is there can be side reactions depending on your starting materials. In this case, we have a, let's see, one, two, three. We have a 3-methyl cyclohexanol. And if you put it in acid, you're going to get an SN1 reaction. And that will produce a racemic mixture. It'll still chlorinate, but you'll get a mixture. And if we try to brominate that alcohol, then we end up with an SN1 reaction that places the bromine on the 1, 2, 3, 4 on the tertiary carbon. Right. So maybe that's not what you want. Maybe it is what you want, but maybe it's not. We just have to recognize that those are possibilities. The way to avoid that problem, rather than using the acid, the hydrochloric acid, the hydrobromic acid, use bromine or chlorine as a compound of phosphorus. So the phosphorus tribromide or the phosphorus trichloride will give you a regiospecific reaction. And this would have to be an SN2 reaction for that first one. Notice that the hydroxyl is on the wedge coming out. And the bromide on the end is going back toward the wall. So that means we had a backside attack, and that happens with an SN2 reaction. Right? We did not produce an intermediate carbocation, otherwise we'd get a mixture. And you get two benefits from this secondary alcohol. Right? We get backside attack, plus it happens on the primary carbon for the hydroxyl. You don't get the chloride on that tertiary carbon like we saw in the previous one. So that's a workaround for halogenating a compound. Plus, the conditions are really mild. You don't have to heat it for hours. You can do it at room temperature. And you don't get any elimination products. All right. So this will be the mechanism for the bromination of our cyclohexanol. And I'm not going to spend a lot of time on that. The electron rich, of course, is the alcohol, and it's attacking the phosphate. And then the bromine leaves, and you've got a bond between the oxygen and the phosphate compound with a free bromide ion floating around there, and it attacks the carbon at the base of that. That's the SN2 reaction. Actually, they're both SN2s. But since the phosphorus tribromide is not chiral, it doesn't matter. Right? It can attack it on either side. It doesn't matter. The bromide leaves, and then the bromide comes back and attacks that carbon on the backside. And the HOPBr2 is a good leaving group. All right. So what are the limitations here? Well, the limitations for using this phosphorus trichloride or phosphorus tribromide have to do with the hybridization of the carbon. You don't get an SN2 attack on an sp2 hybridized carbon. So you don't get any halide formed from the phenol. Rather than the hexanol, the phenol doesn't give you the same halide formed. So don't waste your time. It also doesn't work very well on tertiary carbons, tertiary alcohols, because of steric hindrance. Notice that when you use that compound, if it's sterically hindered, if you've got a bunch of methyl groups around that carbon and the hydroxyl, and this is a pretty big molecule with the bromides and the phosphide around the phosphorus. So the steric hindrance will keep that yield very low. The reaction will happen, but you won't get good yield.
Are you talking about like when it's like 91% or the?
It won't be, oh no,
Yeah.
like less than 1%, if you're lucky. Now, I'm not sure if you increase the temperature, if you can get the yield to increase, but that kind of defeats the purpose, because one of the advantages to using PBr3 is it happens at room temperature rather than heating it like we did with the acids. Okay, so what are we going to get if we have this cyclopentanol and react it with phosphorus tribromide? Well, let's see. The PBr3 is going to target the hydroxyl functional groups, but there are two groups there. The one on the right is a secondary carbon. The one on the left is a tertiary carbon. So because the mechanism proceeds by SN2 attack, secondary carbon is is prone to the reaction, but the tertiary is not because of steric hindrance. So it's going to attack the one on the right. You got this methyl group sticking out here, and you got all this mess in the way. So it's probably going to attack
From the back.
the one on the right. Yeah, we haven't decided front or back yet.
Oh.
But
if it's SN2, it usually attacks from the back there, correct?
yes, yeah, you're right. Oh, well, actually, since the hydroxyl group is on the dashed, it's pointing back, it'll come in from the front, but it's still called a backside attack.
Yeah, okay.
So yes, there's going to be a reversal of the stereochemistry at that site. So this is what the mechanism would look like. It's going to the bromide is then going to attack from the backside, and that means the bromine's going to be out now with that configuration. So we'll produce that stereochemistry over on the right. Okay, how do we halogenate an alpha carbon? We're talking about ketones here. So if we're going to the alpha carbon for a ketone is that's kind of odd. They call it the alpha carbon, but I thought the alpha carbon was where the carbonyl group was. I guess the alpha carbon is the first one you encounter when you leave the carbonyl group. So there's an alpha carbon on the right, there's an alpha carbon on the left. So suppose we want to halogenate that alpha carbon. Right, we're going to use bromine, actually elemental bromine in basic conditions. So the mechanism says that base is going to, we're going to get a proton transfer with that the hydrogen attached to the alpha carbon, and then it's resonance stabilized with the enolate. Right, so once we form that negative, once the hydroxide removes the hydrogen and those electrons then reside on the alpha carbon, then that is stabilized. Now let's see, the enol. The enol is a minor, it's stabilizing effect, but the enol where you have the ene and the alcohol, that top one with the negative charge on it, that's the enol. And that stabilizes the anion, but it spends more time in the carbonyl form. So that's where the reaction is going to occur, even though it's stabilized in that form. And it becomes, since it's it becomes the nucleophile, and it attacks the bromine. And the bromine then attaches to that carbon, and we leave a bromide behind. And this is is this basic conditions? Yeah. So we got hydroxide ions out there. Now we got bromide ions out there. So the ionic balance is preserved. Okay. Then we did that so that we had a halogenated substrate. Right? And there are two possibilities. If we attack it with a nucleophile, then we can substitute the nucleophile for the bromine. Right? It'd be kind of difficult because that's a tertiary carbon. Or we can do an elimination reaction where it attacks the hydrogen. I think the elimination is more likely, right? Because of all the steric hindrance. Let's see what it says. Well, we're going to focus on the bromine. Why did it attack the bromine? Bromine is supposed to be nonpolar, right? But as the bromine, the diatomic bromine approaches that negative, it repels the, it's kind of like intermolecular attractions, right? You have the ions, you have the dipole, and then you have the
London dispersion.
London dispersion. So it's inducing, as it approaches that alkoxide, we get an induced dipole in the bromine. So that makes one side of the bromine slightly positive and the other side slightly negative. And that's why, when we go back here, that's why one of these sides, the positive side, is attacked by the negative side. Okay, so what do we get as a product? Well, if we have an SN2 attack, then we get a racemic mixture of stereoisomers. Well, no. Sorry, my mistake. Because the attacking species, let's see. Wait a minute. Sorry, I'm confusing you. Then, oh, this is a different compound. Yeah, this is a different compound. Okay. It's still going to attack the hydrogen. It's still going to replace the hydrogen on the but we get a mixture of stereoisomers. Why would that be? If it's an SN2 attack, we should just get an inversion. Okay. So let me go back. Oh, I'm sorry. No, that's perfectly all right. The carbon now is not a chiral center. Right? It only has 3 groups attached to it. So when it attacks, it can attack from one side or the other. So rather than being attacked from front or back, it can attack from front or of its front or back. Okay, so that gives us a mixture of stereoisomers. Bromine on one side or bromine on the other side. Okay, now it makes sense to me. Did my jumbling around make any sense?
Yeah.
Okay. Under basic conditions, we can get, and we usually do get, polyhalogenations. In other words, you got the bromine in there, you got basic conditions, and you got the opportunity for, on that alpha carbon, we've got 2 hydrogens, and we can replace both of them. And that's typically what happens. With each additional halogen atom, the remaining alpha protons become more acidic. So actually, the second halogenation runs even faster than the first. So this is the mechanism that you would see, where you get the first hydrogen attacks, brominates, and then that second hydrogen becomes even more acidic, which makes it more vulnerable to the hydroxyl attack. And you just brominate both of them. Now, it's not going to happen on the other side because that's a tertiary carbon. It has no hydrogens. So what if we conduct this reaction under acidic conditions? Under acidic conditions, now we can get a single halogenation, if that's what you want. If you want multiple halogenations, right, do it under basic conditions. If you want a single, do it under acidic conditions. With each additional halogen atom, the remaining alpha protons become less acidic under acidic conditions. So this is what it would look like. We got that one hydrogen. Now, what we approach it differently. In other words, the acetic acid does proton transfer to the carbonyl oxygen. And then we get the acetate anion attacking that hydrogen, which makes an enol form. Right? Now we got the enol form that is stabilized. Then the halogen is attacked with an SN2 reaction. And that gives us, we chlorinate that carbon, and then the acetate ion attacks again and deprotonates and leaves behind the carbonyl. Now let's see, there's no further proton transfer. Halogenation stops here. The reason it stops there, now there's another hydrogen in there, right? We've only got 3 bonds into that carbon attached to the chlorine. There's another hydrogen there. But the electron withdrawing effect from the chlorine atom destabilizes the positive charge. So we don't develop that oxycation like we did in the first step. If we had the first step like that, then we could remove the second hydrogen. But the chlorine now, under acidic conditions, since that oxygen has a hydrogen on it and it's positive, then we further destabilize it by the withdrawing effect of the chlorine. And that makes the hydrogen attached to the carbon, the other hydrogen attached to that carbon, less acidic. All right, so that's the takeaway. Under basic conditions, the second hydrogen is more acidic, so you proceed to another halogenation. Under acidic conditions, that hydrogen becomes less acidic, and you stop with a single halogenation. Okay, here's our epoxides as substrates. I mentioned earlier that epoxides are very, very unstable. There's lots of bond strain in that 3-ring structure. Now this down lower left-hand corner, the one that's called oxyrane, that's the proper name, oxyrane. But you'll often see it labeled as ethylene oxide. And in the medical venue, ethylene oxide is used as a sterilant. You take your surgical tools, wrap them up in their bags, and then put them in this device, and they inject ethylene oxide in there. It penetrates the bag, kills all the germs, and then leaves the bag when you evacuate the cylinder, and you've got your sterilized instruments ready to go. You don't have to heat them up like they used to sterilize them. Now we do it with ethylene oxide. It's extremely reactive, right? Nothing lives. Okay, so let's get back to it. That's an epoxide. And let's see. It can become a substrate. Let's see, I'm not sure why that first one at the top water is a reactant in DMSO, and we're replacing the bromide with hydroxide to make ethanol. Okay. And then if we take under neutral conditions with methanol and the oxirane, we can get 2-chloroethanol. All right, so we can chlorinate one end on one side, and the oxygen opens up, the ring opens up, and we protonate that oxygen, and now we have a primary alcohol and a halogenated compound. Under basic conditions, though, we don't chlorinate it. Well, we're not going to chlorinate it. We're using the methoxy group. All right. Those are just demonstrations of reactions that you can do. I mean, there's nothing special about that. So, that second reaction, we have a primary carbon in the epoxide, and we're going to attack it with that methoxy group. And it's a simple SN2 reaction. Yeah, just an SN2 reaction. We'll add the methoxy, and then the oxygen has acquired an extra set of electrons, which makes it negative. Now it attacks the methanol and removes a hydrogen, a proton transfer, and that produces the another methoxy group. Okay, that looks like it is self-perpetuating. Okay, we started off, we have methanol here, and we have sodium, whatever, methoxy sodium. Okay, so you do need a little bit of it to get started. But you got to have some to get started over here. But once the reaction starts going, it produces more of its own. Right? So you probably only need just a little bit to get going. And then one of the products is this one, and it just keeps going until you run out of oxirane. So the SN2 reaction is, I wouldn't say preferred, but it's possible because of the, it relieves the ring strain. So it happens in a single step. Okay, regiochemistry of epoxide ring opening under neutral or basic conditions. Okay, so the first option is well, that looks like acidic conditions. Neutral, let's see, am I covering something up here? Oops, I need to go back. There. No, it's just neutral or basic conditions. Well, let's see. I guess the ring opening occurs in the first step, which would be considered neutral. So in this particular epoxide, those carbons are not equivalent. The carbon on the right is more substituted than the one on the left. So the addition, the substitution of the ethoxy group will occur at the secondary carbon. I mean the 1, 2, yep. Yeah, the carbon on the left. And then we acidify it afterwards to proton transfer to that to the oxygen that's left over. So under neutral or basic conditions, the nucleophile attacks on the epoxide at the less highly alkyl substituted carbon. Okay, that makes sense. And from the side opposite the oxygen. So if it attacks from the backside, that still leaves this methyl group sticking out like it does up here. And then the ethoxy group is attached there in the plane. Okay. What happens? Well, this is under basic conditions, right? A neutral or basic conditions. Under basic conditions, we get a backside attack. Okay, that's expected. And then we get a proton transfer. All right, nothing special about that. The attack occurs at the least substituted carbon. Yeah, causes steric hindrance. This is called a backside attack or Walden inversion. That's the one where we had that little picture of the umbrella that was flipping one way or the other. All right. Let's see. Major products for this one. What's the nucleophile? The nucleophile is the methoxy group. That's the electron-rich group. Under basic conditions, the nucleophile will attack the less sterically hindered carbon of the epoxide ring. Let's see. Occurs from below the ring. Remaining substituents attached to the carbon flip upward after the ring opening, and the acid is added to protonate the oxygen. All right, so that's the stereochemistry you get. Let's see. The only thing that flips is that methyl group on the attacked carbon. Okay. How about acidic conditions? What happens then? Under acidic conditions, the attack is on the more highly alkyl substituted carbon. So we have hydrobromic acid in water. The nucleophile attacks an epoxide at the more highly alkyl substituted carbon. All right, those are just, that's practical outcome. It doesn't say why. Why does it attack that more substituted carbon? Okay, here's the mechanism. First, we get a proton transfer from the hydrobromic acid. And then you notice that the oxygen is further away from that carbon on the right. The bond strain. Let's see, do I have some statements? Yes. The fast proton transfer is the first step, generating an intermediate with a positive charge on the oxygen. Okay, so we got a positive charge on the oxygen, and we delocalize the positive charge on the protonated oxygen. Both, when that happens, the carbon-oxygen bond partially breaks in the intermediate, indicated by the dashed bonds. So you notice in that central one, we start to get bond breakage. And as a result, both carbon atoms of the epoxide gain a partial positive charge, right? As the bond breaks, the electrons are starting to move toward that oxygen. So there's a fight between the two. Which one becomes more positive than the other? The additional alkyl group attached to the carbon on the right is electron donating and helps stabilize the developing positive charge. So the stabilized positive charge on that carbon on the right means that the bond breaks more easily on that side because the electrons are moving toward the oxygen. So that's why the more highly alkylated, more highly substituted carbon is the preferred carbon for the attack. because its positive charge is more stable. Okay, that wasn't a very good explanation.
It's okay.
And like I've said before, nature just does what it does and we have to explain it. The experimental evidence shows that in the process, we measure the bond lengths, and the bond length on that right-hand carbon oxygen is longer, which means it's weaker. That's why that one breaks, and we get the nucleophilic attack on that carbon, more substituted carbon rather than on the other. And this is under acidic conditions. And the acidic conditions do what? They protonate that oxygen. That's where the mess starts. So if epoxides are so good for as reaction substrates, how do you make them? Because they're not very stable. This is a case where the epoxide probably has to be made right before you use it. So one possibility is form the epoxide from a halohydrin. So that means the hydroxyl group is on one carbon and the carbon right next to it is halogenated. And then under basic conditions in diethyl ether, it takes a long time, you get an epoxide. And this epoxide is on the end of the molecule with a proton transfer in SN2. The SN, okay, this is odd. Not odd, it's unusual. Amazing. Let's put it that way. It's amazing. The SN2 attack occurs intramolecularly. In other words, the oxygen is the attacking species and it attacks the carbon that's attached to the chlorine rather than having two species come in. So it's kind of, I don't know, is it a misnomer? SN2 needs two species, but here we've got one molecule doing the whole thing. Right. So it's supposed to be bimolecular. This is not bimolecular. It's just one molecule closing a ring. Right. So I guess we have to call it SN2 for other reasons. Rather than create a whole new category, we just say, okay, it behaves like SN2, so we'll call it that. And now we've got our epoxide. Diazomethane formation of methyl esters. Okay. So here we have diazomethane, which would be azo, and then methane. Like that. Yeah. That would be diazomethane. If you react and excuse me, a carboxylic acid with diazomethane, you're going to create an ester. And that ester, the methyl group, comes from the diazomethane. No, it doesn't. Maybe it does. It has to be an aprotic solvent. So that's why we have diethyl ether. And we have dichloromethane also in there. All right, so this is the mechanism. It shows what happens here. Did I draw that right? Yeah.
Yeah.
Yeah. It's resonance stabilized. All right, so actually, they say it's more like this. Looks like a Witter ion.
They have the 2173. H2.
Oh, two. There we go. Okay, so once we, well, let's see if that's a negative. Yeah, okay. My mistake. Diazomethane is resonance stabilized. But this one is the reacting species. So plus. Yeah, perfect. Negative. And a lone pair. Okay, so that's the reacting species. And it transfers a proton from the carboxylic acid. So carboxylic acid deprotonated, and it goes in and let's see. Right. It goes in and does it take the proton back? No, no, it attacks the carbon. Right. Okay. So the carboxylic acid is the nucleophile. It attacks the carbon, which is slightly positive. It's electron poor. And that leaves behind the azide. Actually, it leaves nitrogen. Like that. Gas. Yeah. Yeah, we got nitrogen gas, which is a good leaving group. And it leaves behind the methyl group attached to the oxygen. So this is methyl ester formation. I'm not sure if we use that procedure or not. When we were studying mixtures of fatty acids in plant tissue, fatty acids are not very volatile, right? The carboxylic acids are not very volatile. So we wanted to use gas chromatography. And you need a volatile compound or a mixture of compounds in order to use gas chromatography because it's an equilibrium on the stationary phase between condensed and vaporized. So as the mobile phase moves through, it picks up the vaporized and moves them down, they recondense. And the ones that attach to the stationary phase more strongly lag behind. But you have to get them to volatilize. And one of the ways to do that is to methylate the fatty acid. So we would put the fatty acid mixture in these ampules and put in the mixture and then seal them up and then stick them in autoclave and heat them. And it would methylate the fatty acids, and then we could shoot them into our gas chromatograph and use it to separate the fatty acids and do a quantitative analysis. Let's see, amines and quaternary ammonium salts from alkyl halides. All right, so this is just a reminder of what we mean by primary, secondary, tertiary, and quaternary ammonium. If it's primary, there's only one carbon attached to the nitrogen. So I always start with ammonia. Here, 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 like that. So a primary would be, we would attach an R group here. Right. A secondary is we'd attach a different one here, or it could be the same, but I would make it two. And then a tertiary, primary, secondary, tertiary would be another one here. And then if we attached a fourth one, right, and we used these two, this is a coordination bond. We use those two to form the bond. Now we got a positive charge. So quaternary ammonium compounds always have that positive charge on the nitrogen. These are examples of different amines, amino acids, right? We looked at those earlier. Histamine. Everybody knows about histamine. It causes itching. It's actually, it functions as a neurotransmitter. So that's probably why it itches. It's got your nerves aggravated. But it's also an immune regulator. It causes capillaries to become permeable, and it lets fluids come out of the capillaries into the injured part of your body, or the infected part, and delivers nutrients and white blood cells and immunoglobulins to that space. But if it's not controlled and you let it continue, it will send all that stuff into that ring and start damaging healthy tissue. So the body has a mechanism for regulating the histamine. It has an antihistamine pathway. Or you can take Benadryl. Methyl orange is a dye that we use as a pH indicator, right? I think it was on that list of indicators that I showed you at the end of that slide set. And pseudoephedrine. Pseudoephedrine is the original Sudafed. It's very good decongestant, but it's you can get it over the counter, but you got to ask the pharmacist for it, because with just a couple of steps, you can turn pseudoephedrine into methamphetamine.
Yeah.
So they've regulated that. So instead, now they substituted this, the one on the left, the phenylephrine, which is similar molecule, but it's not as effective as a decongestant. And that's always been the complaint. But it's very difficult to convert that into methamphetamine.
So with the like Benadryl, is something, you know how like it makes you sleepy a lot of times? Is that something that happens within us, or is that something that's in the antihistamine? Does that make, am I conveying that right?
It's a side effect.
Like, is there a reaction that happens within us, or is it already like, well, like, is it in the pill and then that causes it? Does that make sense? Like, do we cause a reaction, or does the pill?
The pill causes the reaction in you.
Yeah. Okay.
But the way I'm spitballing here. If a histamine is a neurotransmitter and the antihistamine reduces the histamine concentration, then maybe the histamine is required to keep you alert. And if we reduce the amount of histamine, you reduce the itching and all that other stuff.
Yeah.
But the side effect is you reduce the histamine, and now you don't have that neurotransmitter and you get sleepy.
Yeah. Well, they got the non-drowsy ones now. I was just curious about that one.
Like Claritin and,
yeah.
And Zyrtec.
Yeah.
They don't work very well either.
No, still sleeping.
Okay, so those are amines. They've all got that nitrogen. Let's see. This is a primary amine here. This is a primary amine. Let's see. This is a 1, 2, 3 tertiary amine. This one is a 1, 2, a secondary amine, and this one is a secondary amine. I hope you can see my arrow flipping around there.
Yeah.
Okay. So these are some reactions that we can that can be used on nitrogen containing compounds. We can let's see, they're saying we can alkylate an ammonia. All right, so if we react ammonia with a bromide compound, then we get an attachment between the nitrogen and the carbon of that bromine, and we produce a primary with an SN2 reaction. Okay, that's pretty straightforward. It attacks the carbon on that R group, and then the bromine leaves. And then now we end up with a positive charge on the amine, and another ammonia comes in and picks up the hydrogen, right? Deprotonates it, and that leaves us with the primary amine plus an ammonium ion. And so we've got ammonia in solution, and one of the products that we get from that mechanism is the ammonium ion. And that makes sense because we also have bromide ion in solution. So we got the positive ammonium and the negative bromide that balance the charges. But if we were to write the method out, we wouldn't include the bromide or the ammonia as products. We'd only include the amine as product. So we could take that amine, that primary amine, and it will attack another brominated alkyl bromide, and now we have a secondary bromine by a similar process. And I bet it can continue. Yeah, it can go again and give you a tertiary and a quaternary. Well, the quaternary is trace amounts, right? The majority is going to be the primary amine. And then the secondary amines, I think, probably from steric hindrance. They start to get in the way, so your minor products are going to be the more substituted ones. That we use quaternary ammonium compounds, which is like that. They those R groups could be any length, but they clean fairly well. Right? They clean as well as pure ammonia, right? But they're not as toxic. So quaternary ammonium compounds you're going to find in practically all the commercial cleaning solutions. And you don't want to soak your burette in it because it'll eat the numbers off.
Yeah. Been there, done that.
Learn something there. Okay. So how do we produce a greater amount of quaternary ammonium compounds if we need them? Well, we shift the equilibrium by having a huge amount of the alkyl halide. If we can maximize the concentration of alkyl halide and elevate the temperature so we get a faster reaction with our ammonia, then we can produce a reasonable efficiency for the production of the quaternary ammonium compound. All right, here we got another name. We had the Williamson ether elimination reactions. Now we got the Hoffman elimination. And what does the Hoffman do? Well, we've got our, in this case, we've got a, let's see, well, it's a primary ammonium compound with the amine attached to the number 2 carbon. And then this synthetic reaction occurs in 3 steps. First, we hit it with methyl iodide in excess. Then we take that and we hit it with silver oxide. And then once that's complete, we increase the temperature. So what does the Hoffman elimination reaction do? Well, it produces double bonds. We eliminate the amine and we produce a double bond between two carbons. In this case, we don't produce, notice, I think it was it last chapter we talked about the Zaitsev elimination products? And if it's a Zaitsev elimination, the double bond occurs between the more substituted carbons. So that would be between the number 2 and number 3 carbon. But this was anti-Zaitsev. It occurs between the number 1 and number 2 carbon. And that's the major product. Now, you are going to get some Zaitsev elimination products from here, but the major product is the anti-Zaitsev. So this is the mechanism that we should see. Right, we have that methyl iodide is attacked by the amine. Okay, so we form a bond there, and the leaving group is iodide. That's an SN2 reaction. And that should happen, right? Because the steric hindrance is not a problem with a primary amine. But now we've got that positive charge on the amine, and we're going to deprotonate it, right? So we can, now we don't have a charge on the amine, and now we've got a secondary amine. Plus we've got the, let's see, primary. I'm assuming that amine with the R group on it is just one of the other reactants. And it will proceed through 2 more alkylations. Yeah. And make a quaternary ammonium salt. And in the process, we've liberated the iodide. Now we replace the iodine with hydroxyl. So how do you do that? Well, silver iodide is insoluble. So when you add silver and iodine together, you liberate the oxygen, and it I bet it reacts with water and produces the hydroxyl. Yeah. We protonate that silver oxide, and then the silver combines with the iodine and leaves behind the hydroxyl. So when we add the silver oxide, that removes the iodide. Oh, so this is great. You don't have to do a cleanup between steps because we're adding a reagent that will remove the iodide for us. All right, so the iodide is not in the way anymore. But now we've got hydroxyls. Okay, so the hydroxyl deprotonates the hydrogen off of that secondary carbon, the number 2 carbon. And let's see, why does it attack that one and not the other one? I think that number 4 methyl group is feeding electrons into the that number 3 carbon. So that keeps it from becoming electron deficient. So the next best option is to go to the number 1 carbon, which is electron deficient. Does that make sense? Yeah. So that's why it goes anti-Zaitsev, because of that methyl group. And then, of course, the quaternary ammonium compound is a very good leaving group. Well, actually, when it leaves, it's quaternary ammonium when it's attached, but when it leaves, it's tertiary ammonium. It's a tertiary amine. Okay, that's the mechanism. Now, why the regioselectivity? Okay, now they're going to make me a liar. So we're at the point where we've got that tertiary ammonium in place, and we have two possibilities. If we look at the what's that projection? Newman. We look at the Newman projection, right, where we have the circle and we're looking down the axis and we're watching how those groups interact with one another. We find that the top one, where we rotate around the single bond of, we're looking down the barrel of the number 2 and number 3 carbon. Then we get a lot of steric hindrance in the first one. So it shifts over to the right, where we get both hydrogens are gauche to the leaving group. And remember, the leaving group needs to be anti. I mean, the hydrogens need to be anti to the leaving group in order for an E2 elimination to occur. That came from a previous chapter. Right. So that's why the elimination from between the 2 and 3 doesn't occur. But if we look down the barrel of the 1 and 2, now what they've done, they flipped the molecule around. Right. We had the more substituted carbon on the right-hand side on the previous slide. Now they flipped it around to the left-hand side. So if we're looking down the barrel of the bond between 1 and 2, now we get the hydrogen on the 1 is anti to the leaving group, and that elimination occurs. So that's another way to explain it. That's probably the one you ought to remember.
I'll try my best.
I know it's well, I'm shoveling on you in truckloads. Okay, how do we generate alkynes? Why would we want alkynes? Well, one of the reasons that we might want an alkyne is, say we have something like this. If we can form an alkyde ion, these are very strong nucleophiles. And that will form a carbon-carbon bond fairly easily. So here's how you make an alkyne. Let's see. These are naturally occurring. Falcarinol is found in carrots. And norepinephrine is an oral contraceptive. It does look like a hormone, doesn't it? Either testosterone is probably an analog of estrogen. Tricks your body into thinking you're not fertile, I guess. Okay, the alkynide anion, here we go. So once we've got once we've formed the triple bond, then if we hit that there was a hydrogen out here, right? Just like that. And there's hydrogen out there. Then if we hit it with a H minus, then it'll take that hydrogen off of there. Right? H minus, it'll do like this, form a bond there. This will go over here and leave those two behind, and that's your negative. Okay, then if we react it with a bromide, an alkyl bromide, then a new carbon-carbon bond is formed. I thought we weren't going to do that until the next chapter. Well, I guess we're going to get some of it here. The terminal alkyne, that's what that's called, is weakly acidic and can be deprotonated by a strong base. So we got a very, very strong base there, deprotonating that. Now we have a strong nucleophile in the alkynide anion that can attack the carbon next to the bromine. In an SN2 reaction, the bromine leaves and forms a bond. And then we can do a number of things with it, actually. We can we can turn it into an alkene, we can turn it into a ketone or an aldehyde. So it's very important to be able to synthesize alkynes. And my guess is that if you want an alkyne for a reaction, you don't buy it off the shelf or buy it from a supplier. You have to make it. So that's a
But it's more like pure, I guess.
I think it's unstable. Yeah. Now, of course, this alkyne this alkyne is reasonably stable. We use that in acetylene torches. We just don't draw the hydrogens in there, right? It's carbon, carbon. Right. That's acetylene. But even acetylene you have to handle this very carefully. It has to, all your fittings have to be iron. Can't have any copper because it will
What cause it to heat?
it will catalytically decompose. Copper acts as a catalyst for the decomposition of this, and it will produce lots of heat.
Yeah.
It's extremely exothermic.
Like just on it by itself or when you lit it?
No, it'll happen if it comes into contact with copper. It'll go. Yeah.
So there's like a thermodynamic situation going on.
It's very dangerous.
Yeah.
So when we used acetylene in the equipment, all the piping from the tank to the equipment had to be iron. Couldn't use any copper or aluminum. So that was difficult to work with. Okay, let's see, where was I? Synthesized alkynes. Once you've made your alkyne, you can use it in an E2 elimination reaction. Oh, you synthesize it using an E2 elimination. So we have this alkene, and it's got a good leaving group on it. This is known as a vanillic position. So whenever you have a carbon-carbon double bond, and you have something up here, we're going to use a leaving group. This is the vinyl position, right? It's one carbon removed from the double bond. So vinyl chloride would be like that. And polyvinyl chloride, right? The plastic is made from that. We'll talk about that in chapter 28. That's when it gets fun.
Yeah, this stuff's a little rough.
This is drudge. Okay, so we made our alkyne. We've got a alkene with a good leaving group on it. We attack it with a base. It has to be, we have to attack it with a base because elimination reactions all occur from base attack. And all nucleophilic substitutions occur with nucleophile. Your phone was flashing, is it?
Yeah, I got a text.
Oh, okay.
Yeah, it flashes for when it alerts.
Okay. All right, so we've made our alkyne. Let's see. The leaving group is in a vanillic position. Okay, attached to the carbon-carbon bond. That's good. And then we get a let's see. The substrates, it says, are resistant to nucleophilic substitution and elimination reactions. Oh, so how do we deal with that? Extreme conditions are required. High temperatures, 200 degrees Celsius. That's twice the boiling point. So we're definitely not going to do this in aqueous solution. Try to just boil the water off. Okay, so here's yeah, I was right. Okay, we're using the strong base KOH and heat. That's what that triangle. That delta sign means heat. And this is in methanol and dioxane. Dioxane, I looked that up. Dioxane is, let's see. I think that's dioxane. Believe that's dioxane. I don't think it has any double bonds in it. Yeah. Dioxin has double bonds. You know, the one from Agent Orange. Dioxin would have double bonds in here, and then some stuff out there. This is dioxane, which is fairly innocuous. It's not a problem chemical, but it's a good solvent.
Agent Orange, that stuff that killed a bunch of people, right?
Yeah,
Yeah, okay. That's
it was used extensively in Vietnam to defoliate
yeah, that's what
vast
caused,
areas,
caused like
but it was made cheaply.
the defects. In it.
I'm not sure if it was I mean, it was a combination of 2,4-D amine or 2,4-D acid, one of the other, and 2,4,5-T, which are herbicides. But in the process of making those compounds, you get side reactions that produce the dioxins. If you don't clean it up, or you're not careful with your reaction conditions, you can get a lot of that stuff, and those dioxins are carcinogenic. I mean, these are bad enough, but the dioxins are evil.
Yeah,
And a lot of soldiers came out of that years later with cancers,
yeah,
because the government was buying it on the cheap from a manufacturer who didn't care, and they made the product with lots of impurities in it, because they knew they weren't going to spread it in America. They were going to spread it in some other country.
yeah.
That's one way to defoliate and produce kill zones around your bases. The other way is to drop a daisy cutter. It's this huge fuel air bomb. They drop it, and you can see it go off, and it just blows all the trees down for about 20 acres. Then you go in and set up your base.
That's a,
Okay, back to the topic here. So we got to see, what is the leaving group? Well, in this case, in the top case, the leaving group obviously is chlorine, because that's where the triple bond forms, in that vanillic position. And same thing for the second one, right? Only we're using a different, actually, if you use a stronger base, you don't have to heat it up, right? So if we take the bottom substrate, and instead of using hydroxyls, we use hydride ions, then the elimination can take place at lower temperatures. Well, you can use sodium amide too. That works. Those are stronger bases. So that's probably desirable to do it at lower temperatures. So those alkynes that we formed on the previous slide were internal to the molecule. What if we want to produce terminal alkynes? Well, you got to have a leaving group on the end, and we're going to use a very strong base, sodium hydride, and dimethylformamide is our solvent. And this occurs at the freezing point of water. So that's good. Right? That's even better. But it occurs in 2 steps. The first step forms a triple bond, but it also leaves us deprotonated. So we work up, we use an acid workup, I think, and that protonates. Yep. So in order for the elimination reaction to occur, you have to attack the hydrogen that's secondary to the leaving group. Right, so it has to be on the other carbon. That way, if we put the bromide on the end, then we're going to attack that hydrogen. And in addition to the fact that the phenyl group stabilizes well, I can't say that. It could work on non-aromatic compounds too. But once you form the triple bond, then you still got that base in there, and it's going to extract a proton. Right? So that makes an alkyl anion. Now, if you need the alkyl anion for a subsequent step in your synthesis, then you don't want to do the last step. You don't want to neutralize it with adding hydrogen from your ammonia. Let's see, that was, yeah, ammonium chloride from the ammonium. You don't want to protonate it there, right? But if you want the alkyne stable and neutral, then you would go through that last step and protonate it. All right. More examples of alkyne formation. This is interesting. 1,1-dichloropentane, right? That's not a pentene. That's a pentane. So if we go through the process, we're going to do 2 eliminations to get the alkyne, the pent-1-ine. And similarly, we're going to do that with 1,2-dibromo, 1-phenylethane. But it doesn't give us a mechanism. Okay, that's enough.